All right, and so we're going to be finishing up lesson 6.7 today. We're talking about integral functions, and we did a couple of things with those last time. We're going to continue our work with integral functions today. So the first thing we're going to do today is we're just going to take the concept that we learned last time and extend it a little bit. You guys remember the candidates test, right? That's how you find the absolute minimum or maximum of a function. What you do is you identify the critical values. That's where the derivative is either equal to 0 or undefined. And then you make a table. You put your endpoints in first. You put your critical values in next. You find all the y values, and whichever one is the biggest is the absolute max, and whichever one is the least is the absolute min. And so we're going to be doing the candidates test today, but we're going to be doing it on an integral function. So here's my function. G of x is equal to the integral of f of t from 0 to x. And my goal is that I want to find the absolute min and the absolute max. All right, so the first thing that we need to do then is we need to find our critical values of g. And the way you do that is starting off by finding the derivative of g. Now, according to the second fundamental theorem of calculus, what is the derivative of g? The derivative of g would be drop the integral, drop in the x, and you get f of x. So the derivative of g is this function over here that is graphed for us. So this is the graph of f of x, which also happens to be the derivative of g. So I want to know, where is g prime of x equal to 0? You could also do where it's undefined, but that's not really applicable here. As you guys can see in this, there's no holes, gaps, or jumps, so it's not undefined anywhere. Now, some of you guys might be getting a little mixed up and thinking, well, wait a minute, Mr. Bailey, this is a cusp, but I remember you saying derivatives aren't defined at cusps. Well, you're right, derivatives aren't defined at cusps, but I'm not asking about the derivative of this graph, but I'm asking about the derivative of g. The derivative of g is this graph. Now, the derivative of this graph would not be defined at the cusp. Since I'm just looking at the graph itself, all we would be looking for is discontinuities, holes, gaps, or jumps, and there are none. So there are no places where this derivative is undefined. However, there are places where the derivative equals 0, and that's where it touches the x-axis. So I've got one right here, and I've also got one right here. So my two critical values are at x equals -4, and also at x equals 2. So those are my critical values. Now I'm ready to go ahead and do my table. Now, when I say y, I want to be specific. I'm talking about the outputs of the g function here. Okay? I don't mean the y values of this graph. When you do your critical value chart, what goes here is the y value of the original function, which is g. This graph over here is f, which is the derivative of g. So we want the y values of the original function. All right. So we start with our endpoints. My leftmost endpoint is -6. My rightmost endpoint is 8. And we had two critical values that we're going to test, -4 and 2. Okay. So what I need to do now is I need to figure out what are the y values for each of these points here. So I need to figure out what is g of -6. I need to figure out what is g of -4, g of 2, and g of 8. All right, so let me start with g of -6. So I'm going to be plugging -6 into this function up here. So that's going to look like this. Now, first of all, we're going to do the opposite using property 2, because the -6 is a smaller number, so it should be on the bottom. So I'm going to move that down to the bottom. Now, I don't have a lot of space here, but on your guys' notes, you might want to label that as property 2. Next, I want to find the area under the curve. That's what this represents, is the area under the curve from -6 to 0. So I need to find the area of this piece right here, and I need to find the area of this piece right here. And that takes us from -6 to 0. So we have negative, and from -6 to 4, that's going to be base is 2, height is 1. So that's 2 cut in half is 1. So we're going to have a 1 there. Plus, and then for the other triangle over here, the base is 4 and the height is 2. So that's 8. Cut in half is 4, and because it's a triangle. And it's negative because it's under the x-axis. And so by putting these together, we end up with -3. With a negative on the outside gives me +3 is my final answer. So the first thing I did was I plugged in the x value. And in this case, you won't have to do this in all of them, but in this case, I did have to apply property 2 to reverse the limit, so that the smaller one's on the bottom. And then you just find the area under the curve, and then change the sign of your final answer after you find the sum of the areas. All right, so let's go ahead and continue. I'm just going to keep doing that for every point that's on there. So let's go ahead and move on to the next one. The next one is g of -4. So that means I'm going to be plugging -4 in. So do I need to apply property 2 this time? Yes, I do, because -4 is smaller than 0, and it should be on the bottom. So I need to reverse that, applying property 2, right, like that. And now I'm ready to find the area under the curve from -4 to 0. And so now, like I said, I want to find the area from -4 to 0. So -4 is here, 0 is here. So I'm finding, once again, the area of this triangle. We already did that earlier. It was -4. So the area under the triangles, the area under the curve there is -4. But once again, there's that negative in the front. So it actually comes out to be +4, final answer. All right, let's go ahead and move on to the next one. Now we want g of 2. So this time I'm plugging 2 into the top here. Now this time I don't need to apply property 2 because the smaller number is already on the bottom. So I just need to find the area under the curve from 0 to 2, which would be this little triangle right here. 2 times 2 cut in half is 2, and it's under the curve, so it's -2. All right. And then finally we have g of 8. G of 8 is going to be just plugging in 8 here now, which means I want to find the area from 0 to 8. So all the way over here. Now there's 3 pieces. Now in this case, these two triangles are identical. It's just that one's above and one's below. So those areas are going to cancel each other out. And I'm just left with this area of the rectangle here, which is 4 times 2, which is 8. And so as you guys can see, we have our absolute max is 8. And my absolute min is -2. Okay? Now just for food for thought, not a big deal. You don't need to know this necessarily to get the problem right, but it can help make things go faster sometimes. Is we're starting at 0 every time. So I'm starting here. So whatever the original function's value is at 0, we don't know, but well, actually it would be 0, and we could figure that out. But for now, doesn't matter what the original function's value is at 0. I do know this, is that if I move this far, I'm adding a negative number to it, so it's going to be decreasing in size. And then if I go this far, however much I went down, well, it's going to go up that much because those two triangles are identical. And from here, I'm just adding more. So you can see we're adding quite a bit of area over here and losing and gaining none here. So you know that wherever you started, by the time you get over here, you'll have to be higher, right? Now, in this case, we're working backwards. So yes, this is a negative area, but when you work backwards, you're adding the area. Okay, so this actually would be adding 4, so the area increases, and then it's going to decrease by 2 because now your the area is positive here, but remember when you're working backwards, you do the opposite, so you'd subtract it. So you can kind of eyeball it and just kind of guess, well, I mean, obviously, if I go this way, it's going to be higher. If I go this way, it's going to be lower. Stuff like that. You can kind of think about it and analyze it in that way. All right. So once again, let's review how to do the problem, though, really quick. What you do first is you want to look for your critical values. Now, in these problems, that's actually pretty easy. G is an integral function, and the derivative of G is just the graph that we have. So the derivative equals 0 anytime this function over here equals 0, and that's basically just where it touches the x-axis. So you can quickly identify your critical values by just looking where your derivative graph is touching the x-axis. And then you also include the endpoints. After that, you're just plugging those critical values and endpoints into your original function, and that requires you to be finding area. Watch out for that property 2 as you go, okay? So I'm going to go ahead and throw one of these at you guys here. So this is your homework problem number 1 from worksheet 6.7b. I want you guys to find the absolute extrema of this function. Notice the starting point is different. This time it's 4. But that doesn't really matter a whole lot. It'll naturally work itself out. But go ahead and pause the video here. When you unpause it, you will see the solution. All right, so I've gotten it this far, and I want to share with you guys a fast way to do these now that we've learned the long way. I want to show you guys a faster way to get this done. But first of all, let's make sure you got your table set up correctly. You have your endpoint -6 and your other endpoint +6 and your critical values -4 and +4. And now we want to find those G values. Now I know you guys probably already went through and found them, but I want to show you a quicker way to go about doing this. So the first thing we want to do is we want to find our starting point. Your starting point is when x equals 4, because when x equals 4, we have a value of 0. So it's like our starting point. So this point right here is 0. And that's property 1, by the way. If you guys remember that from 6.3, property 1 says that if your starting point is the same as your ending point, then the answer is 0. So if x equals 4, then we get 0, and that's going to be my starting point. Okay? So the first thing you're going to do is find your starting point. The next thing you're going to do is from there, you're going to go to your next value, 6, and that's going to the right. Okay? So going to the right, starting at 0, we're going to add 3 to it. And that gives me an answer of 3. So instead of, plugging in 3 and, plugging in 6 and then going from there to find the answer, you could really just add the area starting from your starting point. Here's my starting point where it starts at 0. Going this way, we add 3. But now the other points, though, we're going to be going backwards. We're starting at 4, and we're going to go backwards to -4 now. That's my next point. I want to go backwards. Now this area is -12. But since you're going backwards, you're going to do the opposite. You're going to do the opposite. So what's the opposite of -12? It's actually going to be +12. Okay, so there's that. And then from there, we would go back one more, and we're still going to the left. So anytime you go to the left, you are doing the opposite. So when we're going left, this is a positive 1, so I'm actually going to subtract 1 from that now, and that gives me an 11. So you'll notice that these are the same numbers that you should have gotten if you did them correctly, the longer way. But the shorter way is to find your starting point, and then from there, if you go right, add the area as is. If you go left, add the area, add the opposite of the area. Okay? So find your starting point, and if you starting from there, if you go right, add the area as it is. If you go left, add the opposite of the area. Okay, and that's a nice quick way to just get all your answers at once. Okay? And if you want to practice it, what I would encourage you to do is go ahead and go back to this problem here and try it. Find your starting point, and then from there find all your area pieces. And then if you go right, add the area as is, and if you go left, add the opposite, and you should get the same exact answers that I had before. Okay? That's a shortcut. I encourage you to use it. Now, the rest of the lesson, we're going to focus on two specific types of questions which look different, but they're really not. They're actually the same thing. It's just that they're wording things differently. So you'll notice that what makes this problem different is that they're not giving us an integral function. But you will notice they're telling us that we have a graph of a derivative. Isn't that what we had before? And also, they're giving us some information about the antiderivative here, an initial condition, and then they're asking us something about that antiderivative, which is kind of the same thing we've been dealing with before. It's just that our antiderivative last time was an integral function. So what we're going to do is we're going to take this information here and we're going to turn it into an integral function so that we actually can solve it in pretty much the same way we did before. So let me show you guys how this is done. All right. We have a graph of f prime, but we want to find out something about f. Well, how do you get from a derivative to an original function? The answer is integrate. So the fact that they're giving us a derivative and asking us about the antiderivative, that's our clue that we want to do some kind of an integration. So we're going to be integrating f prime of x, and when you integrate f prime of x, guess what you get? You get f of x, right? But let me erase that f of x really quick because we'll get to that in a minute. We're going to turn this into a definite integral. They're giving us one value of x, but they're asking about another. Those are going to be our starting points and our stopping point. You put the lowest x value on the bottom, you put the highest x value on the top. So I'm going to put one here and one here. So that's your setup. So basically just write this out first, f prime of x, putting your lower x value on the bottom, your higher x value on the top. Now, what we want to do is we want to complete the equation. So how do we write that equation? Well, it's going to basically be the fundamental theorem of calculus. So let's rewrite that. It's going to be the integral, we said, from -4 to 2 of f prime. And you guys recall that the integral of f prime is regular f, right? The antiderivative. But with the fundamental theorem of calculus, you write that twice, right? And you subtract whenever you plug in the top number first and the bottom number second. And so that's how you want to set up your equation. So that is our first step. So let me write that out for you, and I would encourage you guys to write it down too. All right, so step one is to use the fundamental theorem of calculus to write out an equation, and that's what it would look like. You would have an integral of the derivative, which is represented by this graph. You're going from this value to this value, which is given here and here. Those are your given x values. And the outcome will be the difference of the two antiderivatives with these x values plugged in, okay, being subtracted. Now, this first thing here, hopefully you guys know what that represents already. That represents the area under the curve, right, from -4 to 2. So we're going from -4 to 2. It's a triangle, so the base of that triangle there is 6, and the height is 2. And so 6 times 2 is 12, but we cut it in half. And let's not forget also that it is under the x-axis, so that's a -6 is that area. So the area under the curve there is -6. So that is step 2. Let's go ahead and write out step 2. All right, and then we're ready for step 3. And in step 3, basically what we're going to do is we're going to plug in all the given information that they give us. So we have found the area, and they tell us that f of -4 is 5. So we're going to plug in the area and this one given piece of information. That's going to help us find the one missing thing that we need. So let's write out step 3, which is to plug in all the given information. All right, so here we go. Let's plug in that given information. So for the area here, we have the fact that that was equal to -6. I don't know what f of 2 is yet. That's what I'm trying to find, so I'm going to leave that as it is. But I do know what that is. F of -4 apparently is 5. So there's that. Now the thing I'm trying to find is f of 2. So in other words, I just need to get this by itself. So I just need to move the 5 over here to the other side. And that's my last step, basically, is just to solve. So as a result, if you add 5 to -6, you end up with -1 is equal to f of 2. And there's our final answer there. Okay, so I'll write out that last step, and there it is. So I'll go through the steps again. So step 1 is set up an equation using the fundamental theorem of calculus. That was this thing up here. Step 2 was to evaluate the integral by finding the area under the curve. That's what we did here. We knew to go from -4 to 2 because of our limits here and here. Step 3, we plugged in the given information. We found our area, and we also plugged in the 5 that they gave us. And then step 4 is to solve it, and we did that just by adding the 5 over. And we got our answer. So f of 2 equals -1. All right. So we'll go ahead and let you guys try one. Let's go ahead and have you guys try one of these things. So homework problem number 2. Go ahead and pause the video here and go ahead and do as much of the problem as you can. And when you unpause it, you will see the solution. All right, so step 1, this is how you would set up your integral equation using the fundamental theorem of calculus. We do the integral of the derivative is equal to the antiderivative minus the antiderivative. We're plugging in x value 0 and x value -6. Smaller one goes on the bottom, bigger one goes on top. Bigger one comes first over here, smaller one goes second over here. And then we go ahead and find the area under the curve and replace this expression here with that area. The area I got from -6 to 0 is -3. We have a triangle over here of 1 and a triangle here of -4. When you put those together, you get -3. So the area under the curve from -6 to 0 is 3. Step 3, you substitute the given f value in this case is the g value. We know that g of 0 equals 9, so I'm going to replace g of 0 with 9. Subtracting 9 on both sides, I get -12 equals -g of x. We don't want that negative in the front, though, so you do need to divide both sides by a negative, and you end up with g of -6 equals 12. So as you guys can see, it's quite similar to the problems we've been doing. We just kind of have to create our own integral function, our own integral equation. And this is our last example and practice problem of the day, example 7. It's really just an extension of what we've just discussed. It's the same problem, it's just that now they want us to go a little farther and actually find not just any old x and y value, any old y value, but now they want us to actually find the minimum and maximum y value. So let's begin here. So first of all, they're asking me to find the minimum and maximum of f. So if you're looking for an absolute min or a max, once again, just like on the first problem we did today, I'm going to set up a table with the x value on the left and the f, or the function that you're trying to find the min and max of, on the right. You're going to put in your left endpoint, you're going to put in your right endpoint, and any critical values. How do you find the critical values? Well, the critical values are where the derivative of that function equals 0, and since this is a graph of the derivative, it equals 0 anytime it touches the x-axis, just like on the first problem we did today. So that's going to be 0 and 4 are my critical values. So those are the candidates for where the possible location of the extrema may be located. All right, now before I begin to finish this problem, there's a long way and there's a short way to do this. So here's the long way. Let me review with you guys the long way to do this. And you might think, well, Mr. why are you telling us the long way? Well, just bear with me for a minute, okay? The long way is to find f of -4. Now the last time we did this earlier today, they gave us an integral function, so we just plug -4 in and we follow the formula. In this case, though, we don't have an integral function. We have a derivative graph, right? So we're going to have to create our own integral function. Now, for this particular problem, they actually tell you the answer to the first one here. F of -4 is 3. That's nice. Didn't have to do any work for that one. How about f of 0? Now we got a problem because I don't have anything to plug it into. So how do I do this? Well, I know f of -4 is 3, and I want to find f of 0. They didn't give me an integral function, but I've got a derivative. So I'm going to write my own integral function, and that's just like what we did in the last example problem. So I'm going to set up an integral of the derivative, and I'm going to plug in the given x value and the desired x value. Now you got to be careful, once again, to make sure that your smaller number's on the bottom. If your smaller number's not on the bottom, then you've got it backwards and you're going to have to flip it. But, you know, when you're setting it up yourself, you should be able to set it up that way. So you don't have to worry about reversing it or anything. But anyway, so there's that. And then we write the antiderivative twice being subtracted, once where you plug in the top number here and the bottom number here. Now what I would need to do then is I would find the area under the curve from -4 to 0. So this area here is 2 times 4 is 8, cut in half is 4. It's above the x-axis, so it's a positive 4. So this area is 4. Next, we're going to plug in the given value. They told me f of -4. Right here, they told me it's 3. Oops. Not equals, minus. So I can replace f of -4 with 3. And if I just add 3 on both sides, I'm going to get 7. Okay? Now that's the long way to do it. And you would just keep doing that for every other x value. You'd do it again for the 4. You would do it again for the 6. And it's probably best to always use the starting point that they give you here, because if you accidentally did something wrong and you solved this and you got the wrong answer and you use that as one of your points up here, that'll cause all your other answers to come out wrong too. So always go back to the one that they gave you. But anyway, like I said, that's the long way. That's the long way. Let me show you guys the shorter way, which is a little bit better. So here's the shorter way. The shorter way is to, first of all, just go ahead and find every piece. So I've got a semicircle here. I've got a little triangle here. I've got a little triangle here. This triangle up here is a +2. This triangle is going to have an area of -2. I've already worked out this quarter circle here. It would be an area of -π because it's under the x-axis and so on. I've got all my pieces there. Next, what do you do? Well, we're going to go ahead and fill all these in here. We want to find f of -4, f of 0, f of 4, and f of 6. And just like we did last time, you want to find your starting point. Only this time, where's your starting point? Well, your starting point is going to be at the x value they give you. So for me, my starting point is right here. That's my starting line. And they told me that y value already is 3. So now I need to go to the next x value, which is 0. So I'm going to go over here, and I'm going to add that area as I go. So if I started with 3 and I add 4 to it, then I end up with 7. Then I go to the next number, 4. So I want to add all the way up until I get here. So now I've got 7 so far. Now I'm going to subtract pi and subtract 2. And if I simplify that, I get 5 minus pi. And then finally, I want to go to 6. So add 4, subtract pi, subtract 2, and now add 2. So if I take my last answer here and I add 2 more to it, I'll pick me up where I left off. And now I've got 7 minus pi. Now this number here, 5 minus 3.14, it's going to be like a little bit less than 2. This number here is going to be a little bit less than 4 because we're subtracting 3 plus a little bit more, right? So I could tell right away this is going to be my max and this is going to be my minimum. And there you guys have it. So once again, you could do it the long way, where you take the given value, put it here, and then just work each one out with your own little integral function. Or you could just go ahead and start at your starting point and add or subtract areas as you go from one spot to the next. Okay. A little bit faster that way. So here's one for you guys. Go ahead and pause the video. When you unpause it, I will show you the final solution. Okay, and so here's our setup. We start off with -5 and 4 as our endpoints. Critical values are where my derivative graph is touching the x-axis, which is -3, -1, and 2. And then for the shortcut, we're going to start by identifying our starting point, h of -3, as -5. And so my starting area is -5. So I'm starting here. Now, the one behind it here, -5, to get to this point, I would have to be going to the left on my graph. So we'll be adding the opposite of the area. The opposite of -2 is +2, so I'm going to add a +2. So if you add a +2 to -5, you get -3. Now, if you want to go up to the next point, -1, on my graph, that would be moving to the right. So we would add the area as is. So I'm going to add the area as we see it here, which is a +1. So I'm going to add a +1. So if I add a +1 to -5, I get -4. And then the next one at 2, right here, is also going to the right. So I'm just going to add the number as is. I'm adding a -1.5. So when you add a -1.5, that's the same thing as just subtracting 1.5. So if I subtract 1.5 from -4, I get -5.5. And then finally, going this way to my last point, 4. Once again, we're going to the right, so we just add the area as is. So I'm going to add 1, and that's going to be -4.5. And now we're ready to identify our minimum and our absolute max. So the smallest number up here is the number that's most negative, and that would be this guy right here. So that's my minimum. The maximum number is the number that is least negative, and that looks like it would be this guy right here. And that is that. So that's the shortcut for finding a bunch of those values really quickly. So that'll do it, and we'll see you next time. Have a good one.